Welcome to Introductory Chemistry with Dr. H. This is a video about equilibrium, and this is just an introduction to equilibrium. So what I'm going to talk about is what is chemical equilibrium and how can we express it. Then I'm going to talk about how does the equilibrium constant change when we vary the way the chemical reaction is defined. And then finally I'm going to do an example. So what is chemical equilibrium and how do we express it? So before we talk about chemical equilibrium specifically, I want to talk a little bit about energy. So we have this sense that things in nature tend towards the lowest energy. And so that's true also of chemical reactions. So in this set of sort of thought experiments, I'm going to talk about this reaction right here. And let me just walk you through it. This reaction involves a reactant A, a reactant B, going to a product C and a product D. This type of arrow, double single-headed arrows like that, one single-headed arrow, right? This is a single head, or we would call it like a fishhook head on a straight arrow going to the left and one going to the right, indicates that this process is in equilibrium. And the lowercase a here means that's the stoichiometric coefficient of A in this reaction. The lowercase b means that's the stoichiometric coefficient of B. And in the products, the stoichiometric coefficient of lowercase c is for capital C, the product capital C. And the stoichiometric coefficient D there is a lowercase d for the product D. So in this general reaction, that's what we're talking about. So if we set this reaction up in reality, like we went to the shelf and we got some A molecules and we got some B molecules and we put them into a flask, and there's some chemical reaction that occurs by this chemical process, we would anticipate that there's going to be some energy change associated with that process. And we can think about the energy change that happens during a chemical reaction in two different ways. And I want really for us to frame all of our thinking about chemical reactions in terms of energy or thermodynamics. So that's why we're starting here. One way we can think about the way an energy changes is we could think about the energy change associated with like one set of reactants, lowercase a molecules A reacting with lowercase b molecule B, those getting together one time and generating the products C, C, and DD. And say, for example, starting material A and starting material B, they start out at a higher energy, and they undergo this process. We're just thinking about one set of them going through that process, and they form one set of products, and those products are going to be lower in energy. It seems to make sense to us that when this process stops, there's going to be more of C and D than there would be of A and B. And that's good. But all this reaction, all this diagram tells us is the energy change for just one set of them doing that process. This kind of energy diagram is called a reaction coordinate diagram. Reaction coordinate diagrams really express the energy changes as one set of reactants undergoes one or more steps to get to a set of products. And so I've just drawn the simplest possible one. But in this case, the starting materials A and B are less stable than the products C and D. Another kind of energy diagram that is coupled to this reaction coordinate diagram is a total energy diagram. When you're thinking about a reaction flask where you've added some A and you've added some B, there are billions and billions and billions of A's and billions and billions and billions of B's. And each time they traverse this process, each one of them is going to have this energy change going from something higher in energy to something lower in energy. But if we think about the energy of the whole collection of them, now we're talking about something called the total energy. And so if we started with 100% reactants, so this is our A and B molecules, that process is going to start going. And so as I slowly move this direction, we're talking about millions and billions of reactions occurring, and the energy of the total system is going to decrease as more of A and B are converted to C and D. And that process is going to continue, and it's going to continue, and it's going to continue until the energy of the total system is a minimum. And what might be a little counterintuitive is that always occurs, that lowest energy point always occurs before you've completed the process, meaning before it's 100% C and D. So even at the lowest energy point, there's still going to be some A and B molecules, and there are going to be some C and D molecules. If C and D molecules are more stable at that position, that lowest energy position, there's going to be more products. So, I've said like 100% reactants and 100% products. So say, for example, that's like 90% products. It's just an arbitrary example here. There's going to be more of C and D as we anticipated, but there's not going to be 100% of C and D. This lowest energy point is what we call equilibrium. So this is equilibrium. And a way to think about equilibrium is the lowest energy proportion of products and reactants. There's some proportion of reactants and products that's going to have the lowest energy. Okay, and so equilibrium always occurs when you hit that exact proportion. And the way we can express this when we're thinking sort of quantitatively about a process is we use this definition of an equilibrium constant. So an uppercase K is what we use for an equilibrium constant for a process. And if we were talking about this process right here, what we do in order to express an equilibrium constant is we write the concentration of the products times their stoichiometric coefficient. So that would be uppercase C raised, the concentration of uppercase C raised to a lowercase c, times the concentration of D raised to that powered lowercase d, divided by the concentrations of the reactants. So here that's going to be uppercase A raised to A, uppercase B raised to B. So notice that the products are in the numerator of that. So if this process, like the one I've written down here, favors the products, the numerator is going to be bigger and K is going to be a large value. So the larger K is, the more products are favored in at equilibrium. So this process is going to start, it's going to go to equilibrium, and when we're talking about that equilibrium point, if K is a very large number, that means we've gotten pretty close to this 100% product side. On the other hand, if K is really, really small, that means that the reactants are favored. And we're going to look at an example like that in just a second. So, importantly on this slide, this is what chemical equilibrium is all about. You have some proportion of reactants and products that is the lowest energy proportion, and we call that equilibrium, that lowest energy proportion. The way we express it is using this equilibrium constant. All right, let's look at the contrary example. Let's say, for example, that the starting materials A and B are actually much less stable than C and D. So as you're going from A and B to C and D, you're actually like asking some reactants to react to form a higher energy product. So this is the reaction coordinate diagram that explains that. As A and B molecules are converted to C and D, the energy of the whole of that single reaction goes up. So now when we're talking about the total energy of the process, if we start with 100% reactants, that's 100% A and B, that reaction is going to progress a little bit to get to the lowest energy point, that equilibrium point, but it's not going to progress very far, because if it progresses far, you're asking the process to move things that are lower energy to higher in energy, and at equilibrium, the things that are lower in energy are going to dominate. So in this process, reactants are favored at equilibrium, and so this equilibrium, this lowest energy point, is going to be close to the reactant side. So in a process like that, now we're talking about the denominator of this expression being large and the numerator being small. And so what that means is K is going to be a very small number. So when K is super small, that means the reactant side is more stable and the product side is less stable. Conversely, if K is very large, that means the products are more stable and thus they're the ones that are favored at equilibrium. Okay, so that's equilibrium and how we express it. And I really think it's a good idea to start thinking about energy. We'll talk specifically about energy in a couple of chapters, but for right now, this is enough to sort of have this sense of how the equilibrium constant is connected to the energy changes undergone in a given process. So let's talk about how the equilibrium constant changes as we vary how the reaction is defined. The equilibrium constant is a constant, meaning once you define what the reaction is, that constant is unchanging. So it's going to be the same proportion of reactants and products under a specified set of conditions is always going to be the lowest energy proportion. But say, for example, we take this process that we were talking about, and we've already sort of defined this equilibrium constant. And just a quick note before we go on, these little square brackets always mean concentration. And so we can't actually express the concentration change of pure liquids and pure solids, because if there's pure liquid there at the beginning and pure liquid there at the end, that concentration hasn't changed, and so we can't track how the energy changes even if the quantity of the liquid changes. So we only include things that we can express a concentration of. So pure liquids and pure solids are omitted from this equilibrium expression because their concentrations don't change, they're fixed. So we can't include them in the expression. They're not part of the energy change associated with the process. Now, to get back to the original point, what would happen if we wrote this process opposite, meaning we started the reaction by putting C and D into the reaction flask, and we knew this is an equilibrium so that we expect some of A and B to form. Well, if we did that, we would be doing the reverse of the original process. And so now C and D would be our reactants, and A and B would be our products. So if we wanted to express the equilibrium constant for this new process, the one that's in reverse, we would have to put A to the A power, B to the B power in the numerator because it's the product, C to the C power and D to the D power in the denominator because those are now our reactants. So I called this one K reverse. So for the reverse of the original reaction, we see that this is related to the original equilibrium constant by just the inverse. So if you reverse the reaction, you have to take the inverse of the equilibrium constant to know what the new equilibrium constant is, K for the reverse. All right, so that's one way we might need to change the way we write a reaction. Another thing that we commonly do is sometimes we have to multiply a reaction by some factor for some calculation that we need to do. So say, for example, we're going to take this original process and we want to sort of do it five times that amount. So if we did 5 times that amount, we would have to multiply each of those species by 5. So the stoichiometric coefficient in front of A becomes 5A. The stoichiometric in front of B becomes 5B. The stoichiometric coefficient in front of C becomes 5C. And the stoichiometric coefficient in front of D becomes 5D. We can figure out what the equilibrium constant for the 5 times reaction would be if we just sort of include those 5s up there when we're crafting the equilibrium constant expression. But then we realize we can just do math and we can pull this 5 out of there. So if we just pull the 5 out, so we have this whole thing to the power of 5, we can see that if we do a reaction times some multiple, it's just the original equilibrium constant to that new power, okay, to the power of 5 if we're multiplying by 5, to the power of 2 if we're multiplying by 2. Okay, so that's the way the equilibrium constant will change in different circumstances where you have to redefine how the reaction is expressed. Okay, so let's do a quick example. Here's a chemical reaction. It's nitrogen dinitrogen tetroxide going to nitrogen dioxide. And you can see the stoichiometric coefficients are 1 and 2. Let's start by crafting the equilibrium expression. We're given a value for the equilibrium constant. Equilibrium constants, by the way, have no units, so we leave the units off. We could write units. Now, we could write units, but we don't. We don't usually write units for them. They're not needed. So what we're going to do is we're going to write this. So what we need to do is we need to write the products over the reactant. So the product here is NO2, right? And its stoichiometric coefficient is 2. So I'm going to square that. And then I'm going to divide by the reactant here, N2O4, and the stoichiometric coefficient is 1, so I don't have to mess with anything there. Okay, so now I've got an equilibrium expression, and I've got the equilibrium constant, which is told us, so it must have been measured at some point. And now we're going to try to address some specific case, right? So in this kind of setup, you have to be given all but one variable, and then you're going to solve for that variable algebraically. So if we know that the equilibrium concentration of N2O2, right, dinitrogen tetroxide, is 0.643 molar. So molar, it's in brackets, so I know that that's a moles per liter. So what we're saying is this value right here at equilibrium is 0.643. What is the original concentration of N2O2? Okay, so let's go ahead and solve that. So we know that 4.63 times 10 to the minus third is going to be equal to what we want to know, which is the the nitrogen dioxide concentration squared, and this is all going to be divided by that concentration we were given. So 0.643 molar. So I've got to multiply both sides by 0.643. So I'm going to take 4.63 times 10 to the third, and I'm going to multiply that by 0.643. And so that's going to give me a number of 2.977. I've got 3 sig figs here, times 10 to the minus third. And that's going to be molar. And that's going to equal, we're just going to leave the units off because that's going to be equal to the concentration of N2O2 squared. So now we need to take the square root of both sides. So I'm going to take the square root of that number on my calculator. Oop, I failed to take the square root of that number. So I'm going to take the square root of 2.977 EE minus 3. And that's going to give me a concentration of, so I'll write it like this, NO2 is going to equal 5.46 times 10 to the minus 2 molar. So that's our concentration. And so now, using this equilibrium expression, we can solve for the other equilibrium concentration. So another way these kinds of problems can be written is you could be given, say, the concentration of both the reactant and the product, and then you can craft the equilibrium expression and back out what the equilibrium constant is. So you really just need a couple of data points, and you can figure out what that equilibrium constant is, right? So this is an introduction to equilibrium, chemical equilibrium, and the equilibrium constant. I hope you found it useful.